introduce Clinton Roy. They are an open source software engineer who has made a career out of supporting researchers, and today's talk is towards editing programs via abstract syntax trees. A round of applause to welcome Clinton, please.
Good afternoon, everyone. I'm Clinton. I'm a software engineer. I work at the Synchrotron in Melbourne. I write a lot of code. I use a lot of editors. I hate writing code character by character. I want to edit code by structure. So that's what this talk is looking at. A lot of our editors do a lot of funky stuff with regular expressions. So the really cool thing that's been really cool now for 20 years or so is syntax highlighting, where your editor will match your code with masses of regular expressions and pretend to parse your code and pretend to know what a string is and what a function call is and what a comment is, and do a technical yawn at you with dozens of colours of all of the different structural elements of your code, as though that is a useful thing to do. I have a history of doing black and white slides. A lot of that is from my history, like the first monitors I was using were black and white monitors at university, so colours were a little bit difficult. I've also had a lot of difficulty with projectors over the years, not showing up colours as they were presented on the screen. So I tend to go monochrome, and that extends to things like syntax highlighting, which I really don't like. Having said that, it's a very popular use case for the stuff I'm about to talk about, so you will be seeing some of that. The proper way of doing this stuff, however, is not to use 100 regular expressions on your code. The proper way of doing it is to use a proper parsing library, exactly the same sort of parsing library that your programming language has at the front of it. Regular expressions are great for matching a line and breaking it up into columns. It's terrible for matching multiple lines. It's terrible for matching differing context and recursive context. Parsers, on the other hand, are great for matching code because that's what they were designed to do. So if we're trying to match code in an editor, we should use a parser. The difficulty, though, is that most parsers are written as though they are going to get the full source code of your program. So they're going to always get the full source of your C program, your Python program, your Java program, your whatever program. And that's something that historically they've always assumed they were going to get, and that means that they've been written in a certain way that makes them very effective and very quick at being able to parse the full source code unit. So my personal take on syntax highlighting is we should not be using syntax highlighting for displaying regular things to users. The fact that I've got a string on the screen, I can tell it's a string on the screen because it's surrounded by quotes. I don't need it in a different colour. I don't need a comment to be put in a different colour. I can tell it's a comment because it starts with a comment character. The things that I want colours to be used for are things like spelling mistakes, things like typos, things like odd uses of languages. So like the typical odd use is C string concatenation, which you can also do in Python, where if you just have two string constants next to each other, the language will join them for you. It's almost always a fault, but that's the sort of stuff that I want highlighted in colour, saying this is a problem. I want irregular things, mistakes and errors to be highlighted. I don't want everyday things to be highlighted in all of the colours of the rainbow. And I think it's fine to turn colours on and off depending on what the task you're doing. If you are reading someone's source code and you're looking at the comments, I think it's totally fine to show up spelling mistakes and typo things in the comments. And then I think it's perfectly fine to stop doing that and turn those colours off. I don't think that I don't think our development lives are improved by constantly having 100 colours being thrown at us. I don't think that is a good use of information. So the basic library we're going to be talking about today is TreeSitter. It is a parsing library that is designed for editors to use. It handles one of the big problems with your standard parsers in that it will handle the code that it's parsing being changed underneath it as you're typing. So it explicitly handles the use case that most of your compilers don't handle very well. So the APIs for that library are designed around being able to provide structure of your code to your editor so your editor can do more interesting things. Built into the TreeSitter project is a bunch of parsers for a bunch of different languages. There's a whole bunch of parsers for other languages that are done in community as well. So already you can parse most of your languages without even thinking about it. And chances are, if you've got a reasonably regular language, somebody's already written a plugin for TreeSitter to parse it. So really just showing that there's a lot of language support there. And for you to add your own language, it's probably not going to be a terrible amount of work. So to motivate the talk, I've got a really small program here, a small C program. All it does is loop over the arguments and print them out line by line. Don't get too hung up on the program. It's not designed to be tricky or fancy or anything like that. It is a really small motivating example just so that we can go through the motions of parsing it and showing you the API of TreeSitter. We will come back to the code as we go through parsing it, so you don't need to memorize it. But we just have the simple main function, and we have a simple for loop, and it just loops over the argv array and prints out those items item by item. So the nice thing with TreeSitter is that the core library and the language extensions, roughly speaking, they're all compiled down to simple C libraries with no external dependencies, which means that you can easily wrap them or call them from other languages using foreign function interfaces with very little effort. You can have plugins installed into your editor, and you just need to install just the TreeSitter library and plugin. And am I getting feedback through that? Yeah. And you don't have to do a lot of work to use the TreeSitter libraries. So that means that whatever your editor is written in, there's probably a language wrapper for TreeSitter. So if your editor is written in, I don't know, C, you can call TreeSitter. If your editor is written in, I don't know, Lisp, there's a wrapper for TreeSitter for that. So I have chosen to parse our C example program with a Python parser. The API is very similar across all the languages, so you are getting a good sense of the flavour of the API here. So we are importing the TreeSitter library, then we're importing the C parser, so that's a separate library. We're instantiating our C language, we're instantiating our C parser, so that's boilerplate code that you have to do for all of your parsers. Then I'm doing a little bit of a cheat here, is I'm writing a function that you give it a file name, it'll open up that file, read the entire contents of that file, and then parse it. So this is the sort of thing that you would do if you're opening up a file in your editor, and you've already got most of the file there, you'd chuck it at the parser and it would edit all of that at once. Further on, we'll go and have a look at the API that you can use when someone's typed in a few changes and how you would update that parsing tree. So because we are parsing a C program and we're an editor and we've got to show all of the characters in our program in our editor, wouldn't be much of an editor if it didn't. What we actually need is, when you're thinking about programs, you want to think about them in high-level concepts, like abstract syntax trees, where we just want to know we've got a function, we've got a for loop, that for loop has a start, an end, and a change, and then it's got a body. So you kind of, there's like 5 concepts that we need in our tree. Unfortunately, the editor needs to keep track of every single character. So what we actually need for the editor is what we call a concrete syntax tree. So every character has a place in our paths tree. So just sit down, relax. You don't have to read this. I just want to show you how complicated a concrete syntax tree for a really tiny program is. So we've written our parser, and this little program imports our parser, parses simple C program, and then it just prints the tree out. So relax, and that's our concrete syntax tree for our tiny little program. Now, for a human, that's not terribly useful, but for an editor, it's really useful. This is written in a style of data structure that we call S expressions for symbolic expressions, or symbol expressions, depending on which history lessons you take. This is a language / data structure / syntax that comes from Lisp, so Emacs back in the day. And the really interesting thing with it is that it defines a tree structure. So we've got translation unit as the root of the tree, and then we've got children of that tree inside the brackets. And if I was to pretty print that out for you, I would need an enormous screen, but we would find eventually all of the things down there, like our for statement, so that's where a for loop is, and that's where the call expression, where we're calling our printf function. So every single detail of our input is in that tree, but for us humans, where we really just want to look at the high-level things like the for loop, we need a way to query that complicated tree to find the interesting nuggets in there. So when you print out the tree, and that's like a debugging form in those S expressions, the really cute thing with S expressions is that they are a data structure and a programming language, and because they're a programming language, they also can be used as a query language. So this is another parser. It's building on our previous example. So we are importing the parser that we made before, we're importing it, and we're parsing the C program. So that big whole concrete syntax tree, we've got that in memory now. And now we're going to do you see the brackets? So we've got a very simple S expression there. We're doing a search inside that enormous big concrete syntax tree, and we're just looking for the for statement. The for statement, that name comes from the particular grammar that was written for C, so that's a keyword in the grammar. Initializer, condition, and update. TreeSetter has things called fields. So if you've got a tree, if you've got a node in your tree and it's got particularly special named things, TreeSetter calls those fields, and they make it really easy to pull out semantically interesting bits of information from the tree without having to parse lots of stuff ourselves. The underscore means match any node. So in our for loop, our initializer is an int I equals 1, but our initializer could be an array initialization, it could be a function call, it could be anything. But for this query, we just want whatever subtree gets matched for those conditions, match it. Whatever type of node, match it. The at symbols is an alias, the at for alias. These are the names to the parts of the query that we can pull out of that query once we get the results from the query. So we can call those arbitrary strings, and that means that later on, when we get the results of the query, we can get the field names that we're interested in nice and easily. This bottom code, all it does is loop through the results in the query and prints them out. Don't worry about the printf stuff, that's a bit ugly. But all it is a list of query results, and we print them out. And I'll show the printing out on the next page. And seeing the results of the prints is easier to understand the printing rather than actually understanding the code. So we had the init, the condition, and the update. And here we have 3 matches, the init, the condition, and the update. The node is the node in the concrete syntax tree that the query has matched. And you can see we've got a node on each of those. I've printed out the sub part of the tree here. So for initialization, we've got a declaration type and a primitive type, and that's the code there. So our node is a declaration type, and the primitive type would be an int. The identifier would be the I, and the value would be a number literal, would be the 1. So what we've done here is we've asked TreeSitter to do a search for the for loops, all the for loops in the code. In our example, we've only got one for loop. If we had multiple for loops, it would give us multiple results. And we can see here that we've got a mapping from the code that we've hand input to the concrete syntax tree back to the line, the rows and the columns. I apologise for that, camera operator. I only just realised I was moving like that. So we've got a mapping from the source code to our concrete syntax tree. We've been able to filter through that the high-level things that we're interested in, which you would get in an abstract syntax tree, and then we can map back the exact coordinates of the interesting things all the way back to our source code. So if we wanted to do structural stuff with our editor, TreeSitter's given us 3/4, 4/5 of the tools that we need to do that. So that's what happens when you load up a file and your editor's using TreeSitter to parse the entire file. As you're sitting there tapping away with keys, little edits are happening to your concrete syntax tree. So this is a little bit of an example. So say we had source, which was our old source string, and say we used some editor macro to uppercase one of the strings in the code. We would then call on the tree, we would say, we've got a diff here. So we want to change these bytes to be these new bytes. And we're basically saying the user has edited the source code, and these are the positions in the source code that's changed. And then when we give it the new modified source, and we tell the parser to parse it, we give it the old tree. And because we've given TreeSitter the information about which part of the tree has changed, it only has to go and reparse just that bit of the tree that's changed. So it's not having to reparse the entire file every time we make one character changes. And that's the fundamental improvement at a algorithm level that TreeSitter has been able to make, which means that it's nice and snappy to use for editors. It's kind of hard to give good examples of that because you've got lots of numbers and you're incrementing rows and columns and things like that. But essentially, the API is you are telling TreeSitter this is the parts of the source code that have been edited, and then TreeSitter, you give it the old parse tree, you tell it to reparse, and it will only parse the bits that have changed, making it nice and fast. So you saw previously where we did lots of arbitrary names in queries when we're searching for things. The TreeSitter developers have decided to make a convention, and because lots of programming languages have lots of really similar constructs, so it makes sense to have a convention on tag names, which is what they call these things. So essentially, for all languages that have classes, which is all of your object-oriented ones. For all of your languages that have functions or method, we use function, we use method. And it just means that if you are implementing a high-level tool on top of TreeSitter, you don't have to come up with your own names for all of these tags for these really similar concepts across different programming languages. So now I'm going to show, so what we've seen now is we've seen the low-level interface that TreeSitter has. We've seen one example of the C parser that's implemented in TreeSitter. And we can see how TreeSitter takes the raw source code, makes a concrete syntax tree. We've seen how we can do queries on top of that concrete syntax tree to get interesting snippets of information, which I think of as our abstract syntax tree. And now I want to show some of the implementations of editors that are using some of these TreeSitter features to be able to, like in some cases, they're just implementing the same things that they've had for a while, but instead of using regular expressions, they're using TreeSitter to parse things. And because TreeSitter is a proper parser, it's going to give you accurate parsing results. It's never going to fluff up on doing the parsing. And the other thing is, because it is a regular parser, it's always going to finish parsing in a finite time. There's no chance that your regular expression is just going to run away with itself because you haven't closed a string, for example, and your regular expression is mapping your, trying to match your entire file as a comment string or a C string or something like that. Because it's a proper parser, all of the parsing times have an upper limit on them, which gives you from a user interface standpoint, your editor won't hang when it's trying to do cutesy syntax color highlighting. So Vim has reasonable support for TreeSitter, NeoVim. You can already do all the syntax color highlighting directly from through TreeSitter. This particular example here, and this is structural editing, this is the stuff that I'm actually interested in. What we've got here is we've got all of the function calls, function definitions, and they've been highlighted here with this fold line, and it means that when you're viewing the source code, it is the implementation of those functions is folded away from you origami style, so you're just getting an overview of the source code. So it's a fairly common thing that code editors have had for a while, but the nice thing here is that this is being implemented with a proper parser that is actually finding all of the functions and not some amazingly complicated regular expression that is finding most of the functions but not all of them, and not all of them all of the time. So it's a small thing, but it is correctness that we're going for, and it's also timeliness. Because it's a proper parser, you'll always get confirmed feedback on whether or not the parsing is finished or not. So I'm not a Vim user. I am mostly an Emacs person, which is why TreeSitter and the S expressions is something that I'm very happy. We have at least one other Emacs user in the house. So Emacs is an editor. It's written in a programming language called Lisp, which looks very similar to the S expressions. Like in a lot of cases, most Lisp that you type is just big piles of S expressions. So there's been a lot more interesting development work done using TreeSitter in Emacs than Vim, but the really important thing here is that all of the structure is being parsed by TreeSitter. So all of these things that I'm going to show you that are possible in Emacs, the bulk of the work is actually being done in TreeSitter. So it's not, the bulk of the work's not being done in the editor. It's just that Emacs, because it is a programming language more than it is an editor, it's easy to hack on these things and try out these things. So the module that I'm going to talk about is combobulate. We know discombobulate Combobulate is the other way around. So it's to make order of things. The really nice thing, when you're doing a demo like this, you really want examples like this, and all of these Emacs examples are great because we can see that bottom pane there, it's actually showing us the parsing tree that's behind this source code. So what it means is that you can still edit this code character by character as you would normally, but you've also got access to the underlying structure. So we can see the cursor is that red square there. So what this demo is moving that cursor around, but instead of character by character, it's going through the tree. So we can see here that we're essentially walking peers inside the tree. So if a node has a peer at the same level of the tree, that's where we're moving. And so we've got the function here, which is an equivalent peer of the const, and then we've got the return, which is an equivalent peer of the function. Now what we do is, and that's a particular key, a hotkey where we found the current peer and we just want to walk the tree going from brother to sister in the tree. Now what we want to do is go inside that tree and find the new peers inside that tree. And the thing that I think is interesting here is that this is a JavaScript TypeScript parser, and we've essentially got two languages here because we've got the JavaScript, but then we've got the HTML, HTMX stuff inside of it. And one of the things that TreeSit is really good at doing is being able to have multiple languages inside one parse tree. So inside one text document, you can have your JavaScript, you can have your HTML, and then inside your HTML, you can have a little bit of JavaScript. TreeSitter is very comfortable having those nested parsed trees inside it, and as long as your editor doesn't get confused, you can use the same structural editing stuff inside those languages and across those languages. Whether it makes sense to do that is another question entirely, because clearly there are semantic operations you can do to JavaScript that don't make any sense to do to HTML. But in this case, all we're doing is walking around the parse tree by peers, but here we step into the return statement, and we're now at a parenthesized expression, and now we found the div, and now inside that separate language we're just walking from the peers. And then we jump inside the contents of that. So that is, I really like these examples because they're showing us the source code character by character, and they're showing us the parse tree. And if you carefully look at the colors, again, colors, I don't know why colors, you can see every time we're moving the cursor around, because of all the information in the concrete syntax tree that the editor has, it knows every character on the screen exactly where it is in the tree, and vice versa. If it asks the node in the tree, where do you start and where do you end, it's got all that information there. This is an interesting thing. You've probably seen something like this in web browsers, where if you open up the inspection portal, so your developer tools inside Firefox, I'm not sure what they call it in Chrome, but I know they've got something very similar, you can select elements of the DOM tree and then widen the scope of that. And it's a really nice, easy way of being able to select certain subset of the display and capturing all of the contents that you want without having to wrestle with the selection cursor on the web browser screen. This is a very similar notion for dealing with code. So at the moment, we've selected the self.layers section, And if you have a look down the bottom, there's an expression statement and a call and a string and a list. And as we go, we just go up the tree. And as we go up the tree, we're widening the scope that we're selecting. And it means that because we're using the tree to make the selection, we're always going to get all of the context of the tree, and we're not going to miss a few characters on either side. And we just keep going. So now we're matching the assignment, now we're matching the contents of the function, and now we're matching the entire declaration of the function. So if we wanted to copy and paste that function, we could go up and mouse click, or we could go into the tree and just select the tree node, knowing that we get everything. Structural enveloping. So this is the sort of thing where if you're doing something where you've got a complicated expression and you know you want to call round around a mathematical expression, or you want to call trim on a long string sequence. If there's multiple brackets in there, it can be confusing to the eye to work out exactly where you want to put the call. But if we've got the parse tree behind it, we can just ask the parse tree, I would like to wrap or envelope this node with a function call. So in this case, we want to wrap the string in something. So we've wrapped the string in brackets there. And that means that we can put that call to another function in there. And then we've found the next node that we want to wrap. We've wrapped it in the brackets, it's moved the cursor to the right things, and we can add in another function. So if you have got something that has a lot of brackets in it, and you're not sure which brackets you're calling, this is a really nice way of getting the editor, the computer, to do the drudgery for you by looking at the appropriate data structure, which in this case is the parsed tree. Oops. So this is dragging. So this is smart dragging. So typically you would mouse select a chunk of text and move it up and down, but you can also do the same thing by dragging nodes around in the AST. So here we've got, so this is a little bit of Python. We've got sounds, which is an array, and we've got sound footsteps. And if we drag sounds down one element in the tree, it's actually going to drag all of those elements down. And we're not having to worry about mucking up quotes. We're not having to muck around with missing commas or semicolons or anything like that. In all of our programming languages, if we want to move the node up or down, it's the same operation in the AST, and we don't have to worry about any syntax stuff. And if we step inside and we want to move the elements in the dictionary around, we can drag those tuples around inside the dictionary, and we get the same benefits of not having to worry about any syntax errors. This is an interesting example of using a query to get multiple cursors happening. So we've got a bit of HTMX typex stuff here, and we realise that we need to change the names of all of the fields in the XML node to begin with data, so they get passed through the appropriate lane. So we have done a search for JSX attribute. We've got a query result which has multiple cursors for each one of the fields, and now we're just importing data dash onto all of them. And we've edited the names of all of the fields. We haven't had to worry about any spacing. We haven't had to worry about accidentally merging two strings together, anything like that, because we've used the editor, we've used the parsed string to do it. We've got an XML tag. It's got an opening and a close. We can edit that node using the edit node function to replace the name of the node, and that will change both the opening and the closing tag in the editor for us. yes, we're still working at human speed at some level. Whoops. So I think that's a really good example of showing that we've used the query to find multiple cursors, and then we're doing the same edit on all of the cursors, and we're editing the node by changing its name, and that will change the name in 2 places. So I think that's a really powerful example of the sort of things that you can do in your editor built on TreeSetter. I would like to thank Mikey Peterson. He has written this wonderful book called Mastering Emacs. If you're new to Emacs, it's a great place to start. It will teach you everything. He is also the main author of Combobulate, and he does a lot of work on TreeSetter. So all of the examples that I've shown here are his. TixZ and LaTeX, of course, for the lovely presentation. And I'd like to thank the Berkeley Mono Typeface for making code examples that you can actually read off a projector. Thank you very much.
Any questions?
Hey, I know that one of the things that makes TreeSetter special is that it can handle malformed code, and it'll just keep running. It won't just error out.
Yep.
So that you can be doing useful things while you're halfway through typing an expression. How does Combobulate deal with that? Is it?
So if you're parsing, so if you've got a C program and you've got some syntax errors, inside each of those nodes there is an error flag, and if TreeSetter recognises that it couldn't parse, it will flag that node as an error, and it means that Combobulate essentially, and this is one of those things where it's very much a user interface question, but essentially the smartest thing to do is for Combobulate to say, I can't do a query on this because it's not a fully, it's a malformed tree node. I know it's a malformed tree node. I won't do any queries on that.
Anyone else?
So if when you're editing, you've got the entire code base in this abstract tree format, has there been any efforts to try and sort of display the code to the user in sort of something a bit more visual or something other than code? And do you think that is a useful thing to do?
I do think that that's a useful thing to do. I haven't seen any good examples of it. I would love to get to a point in time where code linters are not a thing. I would love to get to a point in time where instead of storing a file of characters, I'm literally storing an S expression, and I never have to have an argument about what line the brace should be on ever again. I would love that to be the case. With a lot of the tree viewers, the user interface problem with them is that they don't scale. So you still end up in the same point where if you're writing code at the moment and you've got a large function and it's longer than 20, 30, 40 lines, the received wisdom is that you break that function up. You still get into the same problem with the ASTs and the tree structures where they all end up too large to look at and you still need to break them up. So it's not something that increases the scalability of being able to read and edit code, but in my mind, it means that a lot of fluff that nobody should care about disappears. But I've not seen good examples of AST viewers, and fundamentally, all of the editors we've got evolved around editing text streams, and for them to come up with a good way of having like a flowable graph, it's a fundamentally different problem set. And I don't think you're going to see that sort of AST viewer editor come from the traditional editor space. I think you'll see that come from left field somewhere.
And theoretically, if that did come from left field, that would still be completely backwards compatible with other people on the code base editing and C++, none the wiser.
Yep, absolutely.
Nice.
Yep.
And that will be it for today. Another round of applause for our speaker, please.